remarks from Dr. Lucky. Dr. Lucky, please.
Okay, thank you very much, Bu Ana. Thank you, and thank you everyone who joined in this Zoom. Good evening. Assalamualaikum, Prof. José.
Waalaikumsalam.
Thank you for joining this our guest lecture, and thank you for your willingness to share your knowledge or your experience. Thank you very much. So, yeah, as Bu Ana said, maybe I just want to introduce our group. Let me share my PPT. So I think I hope that we just not only by until this step, but next step maybe we can find some potential collaboration or some joint research. So before that maybe we should know each other. So now I try to introduce for you from about our research group. So can I start now? Okay, Bu Ana?
Yes, please.
Okay. Okay, so this is our research group on hydrodynamic and biogeochemical processes of inland water ecosystem. So since 2020, I'm a coordinator for this research group. So yes, this is maybe some background or some reason why this group is very important. So we know that we all know that the hydrodynamic and biogeochemical of inland water ecosystem processes is a part of the discipline of limnology. As you know that we belong to the Research Center for Limnology and Water Resources, and this is studies change in inland aquatic ecosystem because of the internal interaction of their constituent components and their external influence, such as climate, anthropogenic input, litology variation, and etc. So the component of the ecosystem include, we know that some geological, physical, chemical, and biological factor. So I think, yeah, we can say that this our group or our concern study is some core processes in limnology. So we tend to work in the basic science, but sometimes we also our this support for some applied science, but we focus on the basic science. And the ecosystem dynamics studies include transport and transformation of this component related to time and space of inland water ecosystem. Okay, and this is our scope of the research. We already know about this picture, but some phenomena natural. So some precipitation, erosion, runoff, evaporation, and so on, and some sediment water interface processes, and so on. So based on our member background study, so some of them focus in the hydroclimatology, hydrodynamic processes, or biochemical cycle, including biology, chemical, physical, and physical limnology, of course, here, and paleolimnology. So we try to combine to discuss and work together to to explore how the processes in the some such kind of phenomena in the, especially in inland water, of course. So here is this is past from this paleolimnology, maybe with past study about environmental reconstruction, and this is for present study we the ecosystem characteristic, weight, and transport, and of course the final output we hope some paper or academic papers, and of course some modeling in the future. So I hope based on this some short description, so we can find some potential collaboration next step for with another research group. We try to, because as you know, I also already said to you when we discussed before. So now in our institute, in National Research and Innovation Agency, BRIN, we have several funding scheme, so we can invite some visiting professor. We can invite postdoc or student even or some some joint research funding. So I think this is a good opportunity for us for next step. And this is our team member. So as I said before, that we have variation background knowledge. So we have some psychotechnology, chemical, environmental microbiology, aquatic geochemistry, and even mechanical engineering also we have. Also some in water management, chemical technology, hydrology and hydrochemistry, and so on, geology and paleontology. So now we in our research group I have 13 members, including me 14. So we yes continue study, continue discussing, and some to find a new finding in our environment ecosystem in lake or some river. And of course, I think this collaboration is needed in here. So eventually, I involved in the CIRNET, as I said, the South East Asian Immunology Network. So this I think very advantageous. Maybe here I saw Prof. Wan Masina from Malaysia. Thank you for your comment. So this example, I collaborate with her in Malaysia to some in Tasik Bukit Merah, yeah, in the USM, and in Korea and Japan also some national university in Indonesia. Of course, we have some MOU or some collaboration. So until now, maybe this one example, some ongoing project, some collaboration with Kyoto University in the Kalimantan. Sorry, can we learn about special connectivity of steamboat web at couples of steamboat sets, and with Korean, we also some collaboration to tracing sediment in the Saguling Reservoir in the West Java, and until now still running. And okay, this is maybe more detailed. So this is when I coordinate this group. So I try to build some collaboration and some project together in national and international. So, but unfortunately, since 2020 we have some pandemic COVID, so it is a little bit hard for us to running some project. But at least example, I and Prof. Wan will be in here with USM. I'm still communicating and still finding some chance or some opportunity to work together again to join research, and also with Japan and Korea. So I hope that maybe in this year or next, at least maybe next year, we can start again some project in several locations in Indonesia. So I think also this possible maybe for you, maybe next step maybe we can also some collaboration. And as far as I know that your country also is unique, I think in some subtropics and also tropical, as I know that in the South America is Latin, this is tropical, like Brazil, Mexico is very high biodiversity. I think this is what is the high value for we can get some collaborating research. And not only I mean some collaboration with abroad. So we also some we call a Rumah program. I think this is some internal funding or national funding from our institute. So we have many programs also get some funding from this scheme. So example, I just mentioned two programs that paleontology study at Lake Singkarak in Sumatra, and also biotic connectivity along the Batanghari River basin in Jambi. So yeah, we now we just starting for this remote program from this year. So I hope this is also can running well. And this is some detailed picture of our activities with some collaborators in Japan, in Kalimantan, was Eva, and some this we just one time we survey. So I hope maybe next year we can conduct again some survey at that location in Kapuas. And also this is still running in Korea, but because we have also some pandemic, so now we try to just setting up some monitoring equipment in there, so we can get data routine simultaneous every 2 months. I think we can take some data. So I hope, and maybe this year we can just start again. And this is this is my project in Prof Island. So this is, I think, is very interesting maybe for you, especially for groundwater. As you know, this is in Rote, this southern part of our country, is small island. This is saline lakes. The salinity is higher than ocean, I think, even ocean. So the salinity until 40 or 45. As I know that ocean is around 34 or 35, right? So this is very high salinity and close lake. So no inlet and no outlet. So but some fish, freshwater fish, can alive in this lake. And the other interesting, so I found some springs, water spring. Maybe I don't know. This is because this is karst environment, so some groundwater in the under surface. So until now, we still conduct this kind of survey, and I'm lucky also next year I got some funding also to continue the survey in this location. So this I think very interesting because not so many people come there. It's a remote area. And I say that this is SealNet, is related to the SealNet. So we try also to engage or some contact with ASEAN Costi. This is our strategy to follow some program in ASEAN, which can be related to our group, how we can contribute and how we can involve in the project. So I think we still keep the contact with ASEAN Costi. This is the last movie. This Prof one we can more explain more detail. I hope we can continue again. Maybe of course this collaboration with USM, because we already start from I think 2013. I think from Master. So a long time we have already collaboration. So I hope maybe we can still for next time to can get some collaboration. Okay, and the last, this is our activities in this year. So you guest lecture is a second event. So the first, before we already conduct some internal seminar also with Korean. So I think this is very good chance, and we can share and each other about our knowledge and experience, and then yeah, we can also finding some what is potential for the proposal or some funding for doing this report. Okay, and thank you. And this is our team member. So again, thank you very much, proposing. So, and I forget. So this presentation is I didn't make it by myself. So some part also a contribution from my team members. So this is some information for as information about our research group. Okay, thank you very much. I give this time to Bu Ana. Please, Bu Ana.
Thank you, Dr. Lucky. It was a very nice introduction. I strongly hope that we will have a future collaboration one day. And before we begin to our lecture, I would like to introduce you our very special guest. Okay. I hope you are seeing my screen now.
Yes.
Okay.
Yes, it's okay.
Okay, thank you. Professor Dr. José Joel Carrillo Rivera. I hope I pronounce your name correctly. I practice it.
It's okay. It's excellent. Thank you.
Okay, he got his master as geologist engineering from University College London, UK, and then he received his PhD as hydrogeologist from London University, also in UK. He has many professional activities. He has conducted investigation in Latin America, Africa, Australia on the Tothian groundwater flow system, with production in more than 30 years of bachelor's, master's, and doctoral thesis, and more than 100 publications about TGWFS. He worked as geologist at the Geological Survey of the state of Victoria, Australia, and he was an advisor to the European Commission, the International Atomic Energy Agency, National Council in Science and Technology, and the Mexican 57 legislature. He is a co-chair of the Commission on Regional Flows in International Association of Hydrogeologists, and he received a Life Member Award from National Groundwater Association, USA. And currently, he is a professor and researcher at postgraduate level, Geography and Earth Sciences at the Institute of Geography, UNAM. Professor Jose, it's a big honor for us to have you here with us today. And before we hear Professor Jose's presentation, I would like to give a brief announcement to all the participants that you are very welcome to write your questions or anything that you want to discuss with Dr. Jose in the chat box, or you may raise your hand after Professor Jose concludes his presentation. And for now, I am very delighted to invite Dr. Jose to give his lecture to us. Professor Jose, please, the stage is yours.
Thank you. Thank you very much. Well, first of all, I want to thank Anna, certainly Professor Lucky for inviting me. It's really a pleasure for me to participate in this program. And I really thank you for your interest on the topic. I think it's very nice of you, and I hope that everybody is somehow benefit or get some benefit from this lecture, at least perhaps to have some interesting questions about what is going to do. So if I may, I will share my screen to see my presentation here. Okay, I hope you may see it.
Excellent.
Yes.
Yes. Okay. Well, so I had to start by saying Bismillahirrahmanirrahim, Alhamdulillahi Rabbil Alamin. And I really appreciate your interest and your view, and I hope you have an important contribution as well. Why I chose this topic? Well, I chose this topic because as I have realized during the last few years, I have seen that the approach to groundwater, sometimes it is lean on the classical question-answer scheme. What it means? I mean to say that usually people say, well, the question is this, and what will be the answer? And we have found, and with my students, that when you look up groundwater, really what you see is the answer. You don't see the question. You need to find the question. You need to see what is the causes of having what you have, what you are looking at, to see if you are what you are might be interested in at the end of the road. So why is that? Because usually what you see is the land is subsiding. You have difference in water quality in the wells. So the water quality changes when you start looking at some of the impacts of that. You see that sometimes the wells get dry or appear to be dry, and you see the springs to have shorter or even larger yield, and you don't know why. So that seems to be that is in fact the answer. And what you need to find is what is causing that answer that you see in the field. That's what we say. It is important not to know all the answers, but to understand the question. Because if we don't understand the question, then, well, you just might come up with a different story, and that's perhaps what at present brings us to the confusion, not confusion, the confusion that we have seen in groundwater. So my presentation will start with the need of a conceptual model. Then afterwards we will see some suggested conceptual models reference. We will try to do something very important, which is to learn from post-modern evidence. I mean, what happened in the past, and then to see how the questions perhaps sometimes were wrongly stated, and of course we finish with some conclusions. But here the idea is why conceptual groundwater modeling? Why we need to spend some time doing some conceptual groundwater modeling? Well, basically because the real hydrological work is complex. As you can see, you have different types of rocks, different types of vegetation, different types of soil, different types of water, and so on. So we have to understand groundwater functioning in the environment. And then once we understand that, we need to try to do it as much as possible. So when we start doing any project, we need to have an adequate, to have a solid project proposal, which means we need to have some important project questions, which might help us to reach the correct observed answer. Yeah, and let me emphasize that what we need to find out is what is causing what we see in the field as the answer. You will go, we will start at what is the important fact here. Well, of course, the important fact, as we will see even a little bit further down, we will see, and we will see why. We will see first groundwater, of course, and then we will see why groundwater is important, and also we will see what is the connection, as you can see here, about the groundwater and surface water. You will see along this talk, this perhaps many of you already know this graph, this section, this hydrological section, in which it is trying to represent the main flow conditions in two, let's say, in two different geomorphological features. The one on the right is a hilly place. The one on the left is kind of a flatty area. So this produces different kinds of flows in the ground that are important to understand. Why it is important? Because we are going to see the majority of the water that we see in this, even in the surface, comes from the ground. So we will see that, and that also we have to realize that the area, as you see here, you see my mouse, you see here you might have a recharge area, and then the water will flow and will go and discharge after several years, perhaps hundreds of thousands of years, will discharge in the natural discharge area, which is just around here. For this case, of course, it will be the same on this part. The recharge will go from this area here and will discharge in this low land, in this part here, and so on. But the important part is that this is what we see, is this what we already see in the field. That's what you see. You see the several effects. First, you see this area, which is the discharge area, which is area where you have ponds, as we have seen today. You have lakes, as you have seen today. You have rivers, and all they are the result of having these flows that go in, discharge the waters in this area here, for instance. And of course, you can see that you have a recharge area, but because it has some special elements that show us that it's a recharge area. And then when you study the flow, you study the water that moves around, and you study how the chemistry increases and moves in a very special way. I mean, it is not random, because the point is that you have different flows. Each of these lines shows a different flow in terms of, let's say, length of path, also in terms of recharge place, where the place was recharged. This one has a different place to this, and also the deep, how deep the water flew. So it comes here to one important action, which is to know what is the basement rock there. So from all of that has to be understood. So as we will see a little bit later, so your study area will need to include most of these features. So we will need to be aware of exactly of how fast or how slow the water travels, and what are consequently the water quality changes. We need to know how important is horizontal flow, and mainly very important to compare with vertical flow. Sometimes horizontal flow will take many hundreds of thousands of years, as we see here. But as we are going to see in a place that we show now, we will see that, for instance, one well here will be taking water not only from this flow, even if the well is just very shallow, but it might be taking water as deep as 2 kilometers down. So it is something that needs to be put into the conceptual model, so you will be able to try to see how it is this situation. So from that, you will need to know how the flow will respond if human activity is imposed on. That means, as I just said, you have a well. How is the response of the well in terms of what kind of water is going to get? Because if we think that because the water here travels for many thousands of years, we are going to get here water after 1,000 of years. No, it's just the response will be to be measured in terms of water quality and whatever it is, because recharge, because the water that you get in a discharge area, let's say the water that you get here, is telling you what are the conditions up here. It's telling you from the point of view of chemistry, from the point of view of isotopes, what are the conditions of the water discharging here Or maybe in a well, let's say you have a well here, and you're tapping this water, then this well will tell you what is the recharge, what is the water quality of the recharge, what is the manifestations of recharge in under these conditions. So what is the purpose of modeling? At the end of the day, we are doing conceptual modeling. What is the purpose? Well, first to describe the present, usually a challenging situation, in which the challenge is to define groundwater behavior and the changes made in recent times. Also, we need to do this conceptual modeling to plan a solid program in agreement with the adequate hypothesis. So we need to formulate an hypothesis and to see if this, if what we observe in the field and what in the data we are going to collect in the field are somehow attached or responding to the hypothesis that we have written. Also, we need to change the groundwater flow understanding to try to find adequate and agreeable questions to be proposed. So let me insist, we need to not to find answers, we need to find questions. That will be the main challenge in this kind of view that we have. So, at the end of the road, this conceptual model is meant to represent the observed answer. What makes the observed answer being present in trying to understand it in a compact manner, in agreement with all known relevant information that you have about the groundwater flow, especially in the study area, and mainly also not only in the study area as we are going to see, but also in the regional area. So because we need to know how the whole region impacts the site that we are studying, and certainly how the site that we are studying impacts the rest of the region. So here the scale of analysis becomes very important, especially when we have to recognize that you don't need only to do a local study. You need to know a local and regional study, and then to find out the whole framework of hydrologic properties. We need to find out what are the proper boundary conditions, certainly, as many of you surely know, and how are the inflows and outflows, how are the groundwater flow directions, velocities, and so on, and a specific hydrological control, from where we can put this into simple sketches of maps and cross sections, where not only the hydrological information should be placed, but also you need to put also the soil, what is in the surface, what is the kind of chemistry, what is the kind of isotopes, what are the human interventions in this place, so you will be able to have a much proper situation with a conceptual model that will need to be placed in order to gain the correct question. So we already discussed a little bit this figure, in which it is basically a cross section that might represent anywhere on the earth what is going on, and the geological characteristics will be telling us the scale in which this section is represented. So that's very important to know exactly, as much as possible, the geological conditions of the area. Why? Because most of the time, the study site is just this. We have a very lengthy scheme where groundwater flows, but we only have a very small amount of area or terrain or of land in which we are carrying the study. And we forget the other parts that are beyond the limits of our study area. And then we need to include those. Why? Because we might be affecting other parts, or other parts might be affecting us. That's very important, because, for instance, if we are extracting groundwater here in this small section, surely we might be getting water from below, because there is let's say the continuity of groundwater is very most important in many places. And then, of course, you need to do the kind of sketch, let's say, of what is the geological conditions. Even you might have some doubts, you could surely come across with some reliable cross section with, let's say, with the geological, with the lithological distribution or whatever. But as I want to emphasize again, it's not only the geology that is important there, or the geological framework. It's important also to know the vegetation, the soil cover, the actual chemistry, as we see in this section that is represented especially by carbonates, getting in an evolution with sulfates and chloride. That at the beginning you have much bicarbonates as related to sulfates and related to chloride, but at the end of the flow is exactly the opposite. Basically, is what you tend to observe due to the Chotorabeb situation of describe the flow. And then here, for instance, in this one, we could perhaps change the study area site. The study area site could go down to where it actually is the discharge area of this in this section. And in this discharge area, you will have different compounds. Recharge will be very little. In fact, look, and that's what happens in many areas. When you are here, you look at the groundwater seeping out here, or in springs or in wells, and you will see that it's very old water. Why? Because this water infiltrated all the way up here. And then, therefore, you need to understand that the age of the water there represents precisely the conditions where and when the water was infiltrated into the recharge condition. And that's most important to realize when you put into consideration this type of flow. Or even like this one below, you can see another important fact. In this area of the study, you will see that let's say you are very close to the sea. Well, here you might have a lake, let's say a coastal lake, where maybe you have here your extraction wells, you might have perhaps some saline water coming in, but this saline water is not because of the sea. It's because this flow, after it has been traveling for longer time, for longer distance, and when you get it up, when you induce it into your recharge area, into your extraction area, then you will have the water quality of this well, or this flow will go up, and will go into the extraction wells. And you might be thinking, as we will see later on, that you have seawater intrusion, or also because the irrigation water goes back into this area of extraction, and then you will have what we call return flow. And when return flow is present there, it might be somehow covering up the same kind of situation as if you have seawater intrusion. Certainly, it's most important to know the lateral boundaries, the boundaries of the system, because it's, as you can see, basically the same. The place might be the same when you look it up, but when you see the thickness, if the actual thickness is different, if the thickness goes, let's say, increases, or put it the other way, the response that you might have is not the same if the thickness you have below is 1,000 meters, that it is only 100 meters. The response in the wells, the response in the environment, even the amount of water you are dealing with is contrastly different. So you need to see this situation, because you will have also contrasting chemistry, constructed signatures of isotopes and so forth. So that's why it is important to have a cross section, for instance, with your data. Even if you have many question marks, but it still is best to have question marks than ignore some possibility of some data. So in fact, the actual model of that you might need to construct, that you might need to represent the conceptual model, it could be for anything as a simple equation, but certainly with all of the boundaries and certain conditions, or could even you put it in a text and describe what you think it is, or also could be a three-dimension figure, or could be the old way of the 6th century of the maps that I used since that time. So it is most important that we change the view of how we represent, let's say, the environment, and how we represent the planet Earth, or a certain part of the planet Earth, because the maps are certainly a very basic situation, but they are not enough to try to represent a 3D conception, because it's, as you can see, it's basically a map, is a 2D conception. So sometimes it's best either to do a 3D figure or a section. It gives you much more the idea of what it might be going on. So what you should do with the actual modeling? Well, we have to remember that there are limitations in modeling, certainly. We have to first to acknowledge that and try to work as far as possible beyond those limitations. There is, you have to remember that there is no a uniqueness, and there is uncertainty in the modeling. And then we have also to remember that this not uniqueness and uncertainty in the modeling is meant to be banished when the more of the factors you consider. Because let's say if you do only a modeling of groundwater flow, just flow, only flow, and you don't put chemistry, you don't put the simple chemistry, then you will have no certainty, and then it will be a uniqueness model of what you're representing. So you need to include other variables, especially. And then this brings us to the concept of ethics in modeling. Certainly in the modeling is like the design of the modeling, which is like what happened in the legal cases. We need to try to avoid in both ways the inclination of prejudice or against certain situations. We have to consider whatever is logical to be considered, or sometimes whatever is illogical, and then try to erase it from the actual considerations. We need to see how the evaluation of the results plus the field work, which was designed due to the hypothesis, and then to try to work out perhaps a better conceptual model. Certainly, we have to remember also another important fact, that modeling is certainly not so expensive. Of course, you need to put some money into it, but that is not the actual, let's say, limitation to do modeling, the costs. So, in order to go from the understanding of the question to confirm the answer that you see in the field, we will go through a certain type of steps. We could say, first, of course, we need to define the question, to identify the critical elements and the involvement of the environment, and what are the fingerprints as a matter of fact. Then we need to obtain historical data on the region, from where, okay, because with that you can improve your conceptual model, and then you need to do this kind of, we'll say, we have to find out how to improve the actual conceptual model that we do, and then from that we need to review all of the data that we obtain, from where we can have perhaps to define a better model, either mathematical, physical, analogical, or whatever type of model you have. As I said, you can also have a model in terms of what is written in a kind of text, or in a kind of a set of equations, or whatever you feel more comfortable with. And where you have to set the natural boundaries, remember, and most important here is you have to try to reproduce the pristine conditions. When you do modeling, even if it is not just conceptual modeling, even if it's just what you might say a management modeling, the important matter there is to define the pristine conditions. So that's the initial conditions, but mostly initial conditions, because mathematically could be correct, hydrologically might not be correct if you don't use pristine conditions in the evaluation of the parameter process. And then you have an adequate selection of the fingerprint response. Just it is either by temperature, specific ions, isotopes, and yes, usually the idea is to try to put all of this as an adequate selection, all of them, basically at least two of them, if not all, at least two of them, to be properly included. And then certainly we need to verify the proposed response and fingerprint findings. It is most important to do that. And then we will try to see, just to kind of go almost to the end of the lecture, the suggested conceptual models that we might be looking into. For that, allow me to try to remind you what is the importance of groundwater, let's say in the Earth. The Earth has, in the continents, it has about 4% of groundwater. You look at that in terms of water that is present. The rest is permanent ice, seawater, surface water. But if you see, groundwater is 4%. And the important matter is also something what sometimes people hardly see, is that it's precisely the seawater. It was studied by the International Atomic Energy Agency in study in this century. And in 2007, they produced a report in which they defined that between 60 to 80% of the water in the sea at what moment was groundwater. So that means that only between 20 and 40% of the water in the sea comes from rain. So it was a very important finding that it tells you hope to put into a very good story. From where, so I just try to bring you up the importance of groundwater, even if it is as it is related to surface water. You were interested in that, so it's important to see that you put together groundwater and surface water. Always, usually 99% of the water that you have is groundwater, and about 1% is surface water. And the point is that they are interrelated. It is not that you have it separate. They are interrelated, and then you need to understand them thoroughly, because small changes in groundwater volume could affect very, very, very severely the chemical quality of the water that you are obtaining, the presence of surface water. Certainly, it might disappear. Some springs might disappear. Some wetlands might disappear. And of course, you might have land subsidence as well. So groundwater, you have to remember, is crucial to keep the ecosystems functioning, and is vital for the population and as drought relief. And also, even in arid and semi-arid areas, groundwater is the main source of water. We have to do that. And then I'd like to share with you these interesting slides in which I remember this. I remember seeing this when I was in the secondary school, I think. And in secondary school, they teach you all the currents of the sea. And secondly, it's a very interesting situation, because you just see that, but you don't think that how the currents are. And then when you start looking at with certain detail, you will see that in the sea, you have water going in one direction, and together, according to this information, you might have another current of water going in the opposite direction. And then you might say, how it is? Well, it is like this. If you go into internet, you will find hundreds, if not thousands, of photographs showing this situation that, in fact, has been present since the 7th century. Many of you already know that Allah released the two seas to meet side by side, and between them there was no barrier. But there was a limit which is not so far seen. And it is not only in terms of, let's say, in the sea. You see this surface water behaves the same way. Here you have two rivers coming from different subcatchments, let's say, and then of course they have different loads in silt, for instance, and then when they get together, they don't mix. And if they don't mix, it will be the same as this one, as like the Danube. The Danube River doesn't mix neither. The Danube River has several components that has been studied by the International Atomic Energy Agency, and gives you something like this. Why? Because there is water coming into the river from different places and flow across here. And let's say what we kind of present in this sketch, just like a kind of draft, simply to show that what and how we have surface water that apparently might be just one body like this, but because it has not the silt and so on, it might for us appear that it is just one body of water, when it is not. Most rivers have several, let's say, parts of water, as we see in this whole section. And then, okay, we go to trying to see about learning postmodern evidence, which implies postmodern, in which we see now how the importance of what we've been talking about. For instance, in this case, in the US, it is in Florida, in the Biscayne Bay, and then as you see here in this graph presented by the USGS, it's not just any chart there, it's just the USGS, and then here you can see that the chloride, let's say, concentration taking in all of these points, on these points where sampled at this depth, they were constructed, these wells were sampled to take water and then analyze it. And then they got this kind of interpretation of the distribution of chloride in this profile. And from there, they start making this interpretation that what happened is that the sea water is here, the sea water comes and then goes diluted, kind of diluted up. Well, it sounds very interesting, but they forget a couple of things. One of them is that the base of the Biscayne aquifer, it is not impervious. because here they considered it impervious, as you can see, due to this the structure of these lines is considered it as impervious. But then that means that the flow flows only parallel to the impervious terrain. But when you take the groundwater heads, for instance, and you take the groundwater heads for all of these places in which the groundwater was collected, then you can see that what is being considered the base of the aquifer, of the aquifer formation, then what really it is, as you can see, you remember you have flow from a higher value of hydraulic head towards a lower value of hydraulic head. So that means that the flow is going in this direction, not in the direction that the USGS was trying to tell us it was going into. So it is an important issue, especially when you see that you shouldn't try to do a separate analysis of groundwater quality and groundwater heads. You need to incorporate it and understand it as far as possible and to include the proper boundary condition. Another interesting case is, which was in Tenerife, there in the interesting islands in front of Morocco. There was it was a place where you have, or they have, let's say, some chloride placed in the 1992 with this kind of distribution. But then the same chloride in the same wells you have from 1999 the chloride increase. The chloride concentration increase in both in the space and in values, because as you can see now, it is much salty, the water that is being withdrawn. And certainly, as you have sea here, you have the sea there, you have all of this is the ocean. Then the automatic, let's say, the automatic classic and very direct response was this is seawater intrusion. When you start revising the data, you see that the nitrates at that time, let's say in the 1992, well, there were some values, of course, yeah, already above the natural values that you expected for groundwater without being contaminated. But 1999, yes, the values increased drastically. You have values even of 500 milligrams per liter of nitrates. So why is that? For a start, the water that we are dealing with is contaminated water. So what is the let's say the sketch that might explain us a little bit about that is that if you have the flow as it is going on in this area, you might have different flows according to the different topography situation. And then what you have is you have the irrigation, agriculture activities, and then certainly you are withdrawing the water into the wells, and the wells, on the wells you irrigate, but as you irrigate, you put water into the irrigation, and the irrigation sips the water down, and then what you have is certainly two effects. The first is you are inducing a little bit more salty water from beneath, and then the second is you are inducing nitrates from the return flow from the agriculture area, which is very important. That's the explanation of what happened. It is not really seawater intrusion, and then it is just basically something similar was found in Mexico, in the Gulf of California, in Baja California, where in the 1950s, 60s, the water level was not below the level of the sea, but by the 1970s, the water level in the groundwater was going down a little bit in some areas. And then by 1996, it was dominating this situation. The water level was below the sea level. And then when you compare the areas, the effect of dissolved solids, it is very interesting because as you can see in 1960s, 1970s, there were some small places in which you have like saline water coming in, but it is difficult to understand how these were seawater intrusion in these places. And if the same happens in 1995, it becomes a little bit difficult to understand how these places have high salinity, and then how the seawater, if you consider the water moves from here, from the sea towards the inland, how the saline water went through without passing through the fresh water there. And when we ask the water, what is your story? What is your history? What happened to you? And then we see the actual analysis of chloride, which is supposed to be telling us that the water is coming from the sea, and the nitrates, which is telling us the water is simply the situation of contaminated water. And then when we see the number 10 here is the background level. These waters are supposed to be within the background level. So that means that these waters are not contaminated. And as you can see, the waters that are not contaminated have very little chloride. And the water, maybe this one might be high chloride, not contaminated, but maybe this water here with 1,200 might be seawater intrusion or chloride coming from the sea. But the other ones, it is a different story. They respond to the irrigation effect, and also to another important thing. This sample here, it tells us that is the groundwater, the deep groundwater in the area. I mean, water that has not been subject to rapid flow because of this sedimentary area. So that tells us that the seawater, it is not a condition for all of these samples, basically. Another important fact that is also telling us some nice story is when we take a couple of wells here in Mexico, in the area of San Luis Potosí, where you can see that this is the lithological structure of the well. Basically, simply volcanic ashes in one way or the other. Basically, let's say all of the column becomes like that, and some clay. But then what happened in this well? They are getting 45 liters per second, and when you take samples at different times during, let's say, 24 hours, you will see that the temperature in the well is the same, the electrical conductivity is the same, the fluoride constituents is the same, sodium is basically the same. But in this other well, in which we have, let's say, different material. Remember, this one was plastic material from volcanic origin, and this one is volcanic rocks, basically ignimbrites here. And then sorry, these are rhyolites, and here are the ignimbrites. Here you have the rhyolites, and the rhyolites are fractured. So you start taking water here, and look, it's only 5 liters per second. In this one is 45 liters per second. And here is just a very small a very small yield, and this 5 liters per sec produce that the water start increasing this temperature, electrical conductivity, fluoride, and sodium. In fact, the deep water because now we know it, deep water gets there from almost 2 kilometers down in about 2 hours. So it is telling us that the vertical component of flow is most important in this area. And then we just go to almost the previous to the last example I want to show it to you, which is a place in an arid region in North Africa, in this case is Morocco, where, well, certainly you have two important features for this. Of course, you can see it is this line here is the basin, the Dra basin in the Atlas Mountain, and this area here, the Dra, it's a very important feature because there is agriculture, people living there, tourism, and several other matters. But the important fact that we see from the geological point of view is that here you have this red rock are nothing else than the basement rock. And there are close to the mountain, you have the limestone. All the Jurassic limestones are present here. Then what happened? It was a model done. Let's say part of this situation was was introduced. All this data was introduced instead of doing it as on a sketch. We tried to introduce it on a model. In this case, we use the model flow, and in the model flow, we put all the data which was from the topography, the hydraulic properties, the observation wells, the initial heads, the soil vegetation were included indirectly as indicators of discharge zones, and certainly the basement rock. It was all that included, and of course the chemistry, the water chemistry was also of some part for the modeling. And then from that it was constructed this situation where certainly the recharged areas are characteristics of the soils, cold water, local flows. And the discharge areas, we see alkaline soils, we see thermal water, and we see certainly evidence of regional flows. And all of these little arrows are the ones that the model produces by itself. So it is nothing to do with our, let's say, trying to get up here. Here it is the final definition of the flow in Lake Eriki. So, but what did we do with this? It was something important, trying to define what will happen, or what will happen if the recharge is 50 millimeters, and what happens if the recharge is 200 millimeters. And from that, we found that if the recharge diminishes to 50 millimeters, it will only be affecting in the context of the lines shown in yellow, and the flow, let's say the potentials in the lines showing in blue is when you have 200 millimeters of infiltration, so or recharge. So as you can see, in the long term, the recharge doesn't get affected, or the regional flow doesn't get affected by the difference in recharge. What is affected is the local flows on the top, which are manifested by these yellow lines. And then just to end up and going into the questions and comments, we have to tackle a little bit what happens in Mexico City with the subsidence. Subsidence is seen as the result of extracting water. That's it. Nothing else. Nothing else. Well, some people say, well, there may be other things that are important, but the main important matter is how much water are we extracting. And then, of course, that will be one thesis. But there is another thesis that should be put into consideration, because it simply means that due to the conditions that we have at present, there is a non-saturated part between the confining area and the aquifer material below. So what it means, that the water that is being, let's say, induced from the confining area towards the aquifer is being reduced drastically. And then we found it just by, well, I say by Allah's destiny, because when we were looking at some data in one of the offices in the government, we found that in the 1980s, the subsidence velocity in one part in this Mexico City was going from about half a meter to 25 centimeters a year. It was the subsidence rate for the various points of measurement. But then, interestingly, in the next let's say 10 years, the subsidence velocity diminished from 28, almost 30 centimeters, to about 22 centimeters. So you compare these two numbers are very much different. And also when you compare what we saw by the year 2000, even there was a positive rebound. So what it means that subsidence velocity is reduced due to new unsaturated conditions. What means unsaturated conditions? It means that the water table is now here, and before this water table was to be up here somewhere. And now, as it is going down, all of this area here, all of this area is unsaturated. So that means that the water that was migrating from the confined area towards the aquifer and then from here to the wells, it is no longer working that way. Why? Well, simply because of this graph that I'm showing you here. It shows nothing else than the hydraulic conductivity and the saturation in the soil. If you have 100 saturation, you have this hydraulic conductivity, let's say, for sands. Sorry if it is in Castilian, but it is sand. If a sand might have about 1 to the 10 to minus 2 centimeters per hour, sorry, per day. You see, you have that. Sorry, 1 to 10 to the minus 2 centimeters per second. So this 100, yes, per second, centimeters per second. So you have this velocity for the hydraulic conductivity. But if the saturation diminishes, the saturation doesn't diminish in percent, diminishes in orders of magnitude. If you have, let's say, a saturation of 40%, the hydraulic conductivity goes down to 1.2 4 tenths to the minus 4. So the water that might be flowing from here to there might be reduced in 2 orders of magnitude. Okay, which is most important, and then what we see, the reduction in subsidence, and then of course we can trace that through other means by the measurements done in the field and the measurements done in the field in terms of unsaturated areas and also in terms of the subsidence rate. So with some concluding remarks, I will say, just let me tell you that a conceptual model should be created with most environmental evidence related to the components of groundwater flow. And if we do that, we must likely to have a very close condition to support the hypothesis that we're looking to resolve. And then we will try from that to look at the correct, that maybe have more ideas that we might be looking at the correct question. Why? Because all of these correct questions will be in agreement with the observed field data that we have done. We should try to avoid prejudices. They should be placed in the proper time scale and time, because it is, you know, usually, in general, humanity, we will say, tends to put forward what other people thought 10 years ago, 20 years ago, 30 years ago, 100 years ago. And sometimes they feel it as it is a proper way of stating what you feel now. And many times it's not the occasion. Many times it doesn't apply that way. But if you have any doubt, you have to try to apply, let's say, to try to induce each factor by itself, and considering in the application of the observed groundwater response. So I mean, when I mean each factor is what is the physical, that means the geological, the hydrological, the hydraulic heads, chemical, the isotopes, the soil, the vegetation, and so forth. You have to consider that be in agreement with what you observe in the field. So groundwater functioning is most important. You have to look at it into how it is manifested, and especially now when human intervention is being there. Why is important to remember human intervention? Because human intervention is speeding up what was already perhaps a natural movement, slow movement. Now it is very fast. Why? Because human has made it being that way. And then any conceptual hydrological flow model needs to be supported by as many topics as possible. So please remember that, because that way you should be able to tell that your model has as much more support as possible. And then why? Because each of the concepts has a story to tell. Each of the available data has a story to tell. And that story should be basically the same for all of the different components that you are using there. Okay, well, shukran. And please don't forget that in the haste of master the how, which is what happened now. Now everybody is looking at how to model this, how to model that, how to use satellite imagery, how to use this. And then in that way, they have been forgetting the why. They have been forgetting the meaning. Oh, again, shukran, and any questions, please, I will be delighted to try to answer.
Thank you, Dr. Jose. Alhamdulillah, it was a very nice presentation. We are lucky to have you here. Once again, I say. And for all the attendees, if you have any questions, you can raise your hand. And if you want to ask in Bahasa Indonesia, it is very welcome. Do not hesitate, we will help you. And I will see in the chat box, we have a question from Ibtisam. Hi, Ibtisam. Assalamualaikum. Nice to see you again. Ibtisam is asking if groundwater represents 99% of water in the continent. So why the majority of the scientific paper talk about the scarcity of groundwater and the overexploitation of wells?
Well, thank you, Ibtisam. That allows me to talk a little bit more about this topic. Yes, it is. I would say it is an economical issue. And why it is economical issue? Because let's say, just think for a moment, what we are saying here is that groundwater is plenty. there's plenty of groundwater. The only problem that you have is you need to understand how groundwater functions. And once you understand groundwater functions, you are able to try to get it in a way that is sustainable. That's why the title of what groundwater sustainability is somehow. And if you suddenly said, or someone say there is no groundwater, there is no water, the actions will be a lot different. I was at once talking to the director of the School of Economics in Colombia, in a university of Colombia, and I remember that I explained this situation to him, and he said, "Oh, I see why they don't want your proposal being accepted." And I said, "Why?" He said, "Because you are telling that there is no such a thing as a scarcity. You are telling what you need is to understand how to get water from the wells in a proper way. That the actual limitation is not in terms of water, it's in terms of knowledge. How much knowledge that you have, so you might be able to get the water in a correct way, affecting the least people, affecting the least of the ecosystems, affecting the least of humanity." And then, because he said, pointed out the other way, he said, "Look at this way. Do you think," he asked me, "do you think diamonds are expensive?" "Oh, yes, of course they're expensive. But what would you tell me if you demonstrate even more, if you demonstrate, you show me that you lift those rocks there, you will find diamonds. You leave the other there, you will find diamonds. You live there, you will find more diamonds. What will happen with the price of diamonds?" It's the same with water. If you see, all of this situation is a very important effort, extremely important effort, to try to convince people that we have no water, that we are running out of water. That's the trick. That's the trick. If you look at what happened, for instance, in South Africa. In South Africa, 3 or 4 years ago, when they say it will be the day zero. They say are using that here in Mexico, the day zero. What is day zero? Oh, when the dams are empty. Of course, yes, the dams will be empty, but you have groundwater, my friend. If you have groundwater, you have 99% of more water than you have when you are referring to fresh, to the surface water, right? And so they're trying to hide that, and by hiding, and then by making this manipulation on people, trying to convince them that there is no water. So it is just a plain business. And in fact, this matter of overexploitation comes to the same thing. In Mexico, it's just an everyday, let's say, concept that anyone who praises himself or herself being a good person understanding groundwater, if he doesn't say, or she doesn't say, overexploitation, resource, availability, and so forth, it seems that they are not talking sense in terms of water. And it is the contrary, if I might say. Thank you for the question.
Thank you, Dr. José. Amazing. Okay, we're supposed to end at 11:30, but we received several questions from Dr. José. So I hope it is okay if
for me it's okay. For me it's okay.
Is it okay if we
extend? Okay, yes, surely. I have not this opportunity every day, so I might as well.
So maybe the 10 to 15 minutes we extend our meeting today.
Please feel free.
We have another question from Dr. Fajar. I would like to introduce him to you because he is one of groundwater expert in Indonesia. So his name is Fajar. It's mean down. He wrote his question actually in the chat box, but I hope he can deliver his question directly
Please, I
to
will be
you.
most pleased to meet him. Sure, thank you.
Dr. Fajar, are you here with us? Okay, I don't see him. Okay, maybe we wait for him. While we wait for him, we can go to next question from Gumila.
Oh, here is Dr. Fajar. I think
Hi,
you.
hello.
Okay.
Hi, nice to meet you. So maybe sorry, so
Thank
a little
you.
bit noisy in here, so I hope you can hear my voice, or maybe you
Yes.
can read the question, Anna. So a little bit noisy in here. I'm sorry. So please.
Dr. Fajar question is, he's asking about your experience. Should we separate confined and unconfined system for a regional groundwater basin conceptual model? For example, conceptual model for nitrate groundwater flow model and subsidence model. Thank you. And he said, look, it was a very nice presentation.
Yes, thank you. Thank you for your question, Dr. Fajar. Yes. You know, the theory of groundwater flow by Joseph Todd includes, and in fact, many other people's work go into the situation that these particularities of having confined condition or unconfined condition or semi-confined condition, it's just a concept that needs to be dealt with in his peculiarity, in his local scale. In general, when we are talking about groundwater flow, perhaps the best is to see everything as tried to post in these cross sections. I didn't put, as you notice, I didn't say here we have one aquifer, here we have an aquiclude, here we have an aquitar. No, everything is the same. Why? Because what we found is that groundwater could flow from one aquifer to another aquifer below, and then move horizontally, and then go up and flow again to the first aquifer, again, but in a different position. So it's, let's say, I will put it this way, the term aquifer is an important issue because this term allows us to withdraw water from the ground, because it is the conveyor, is the canal, is the let's say the stream that allows us to catch the water in a well, the aquifer. But what we are catching is the water, and then the water moves along this aquifer and or along other aquifers, and then that becomes the important issue to understand. The important issue to understand here is the movement of groundwater, how groundwater moves from one aquifer into another, disregarding that it is confined, semi-confined, or whatever. I don't know if that answers your question. Otherwise, please tell me.
Okay, thank you, Professor.
And then the other part, because you mentioned, sorry, Professor, you also mentioned something about the subsidence. Could you tell me what is the question? Because I know that in Jakarta you have a very big problem with subsidence. Something similar perhaps to what happens in Mexico City, or even more, because here if subsides, well, you can sort of drain the area, but in Jakarta it's the sea is let's say is asking for his place, the place that you allow him to have. So it is a different condition, certainly. But I wonder what is what you really would like to find out, Professor. Please.
Yeah, So I hope you can hear my voice. So okay, yeah. Is it clear, my voice?
Yes, yes.
Okay, so yeah, I also understand that I also understand that you have also a subsidence problem in Mexico City. So that's why maybe you can share how about are you already make a groundwater model for the Mexico City land subsidence? So in that case, so if if you are make this model, you make a regional conceptual model, or you can make separate for some aquifer type system for mitigate the landslide in the Mexico City, Professor?
Yes, yes, there have been some, let's say, a colleague of mine made a groundwater model for subsidence in the southern part of Mexico City, in Chalco. In fact, two colleagues, one rest in peace, the other one is still going on. And the results were basically showing that the subsidence will continue due to the nature of the formations, of the rock formations, which is a kind of clayey stuff with a very important condition of about 60 to 70% of water content. It is just very important. It's about from 60 to 70%, even more water content, because it is the result of a very specific processes in nature. And then what happened with the subsidence here is that even if you stop in this place subsidence, sorry, even if you stop in this place the extraction that is producing the subsidence, it will take 10 years before subsidence get to a minimum. So in actual terms, it is not that simple to have it. Why? Because the conditions beneath the city are different from one place to another. There are places like the one I show you here today. It is also in the south, but not so much to the southeast, but just a little bit to the south in a place called Xochimilco. And the other one is in a place called Chalco. And the response in these two places is very contrasting. In fact, the response in all of the system in Mexico City is very contrasting. It's not the same. And the point here is that all of these studies, well, are being carried out, but with a different view. They don't. They are done with a view of how we say it is soil mechanics. Soil mechanics without applying soil mechanics. That sounds interesting, but that's how it goes. And I tell you because they don't pay much attention to these unsaturated conditions. But if you wish, I could send you some papers in which the main, let's say, the main objective is to try to highlight the subsidence from the point of view of the amount of the water that has been extracted. In fact, that goes back, I will say, to the original question by Ibtisen Yahaoui, is that the point here is that they want to convince us that we are not to take water from the ground. That's the basic idea. Some people want to convince us that we shouldn't take water from the ground, without giving us the alternative answer. That's the other interesting fact.
Yeah, I think it must be very interesting to share because also in Indonesia we have a different characteristic from Jakarta and another part of the northern alluvial system in Jawa. For example, in Semarang and Kalongan, they have a different characteristic based on here. Maybe also in this group there is Dr. Sarah. So Dr. Dwi Sarah, maybe you want to add some comment for Professor Joe?
Please.
Discussion?
Before that, Dr. Jose, could you please stop your share screen?
So, okay.
And also, I would like to give a short announcement to all the attendees. Please fill the the attendance that sharing from one of my colleagues. And Doctor, is there anyone want to raise their hand? Because we have less than 5 minutes more. So
sorry to dominate the discussion. Maybe we
That's
can
okay.
make another session, Professor. Thank you very much.
Yeah, that will be great. Okay, because
Sorry.
we still have several questions here. I will read. Perhaps it will be the last question. I'm afraid it will be the last question. And
don't worry. I can go. You can go. You can go for another 20 minutes. So no problem.
okay,
No
but
problem.
if
No
we don't
problem.
have enough time, I will copy the other question that has not been discussed yet, and I will send it to you by email. And perhaps if the participant send their email to us, I will email them the answer. Okay, and before that, I'm seeing the head of research center for limnology and water resources also with us today, Dr. Hidayat. Thank you for coming. And then there's a question from Gumilar. He is a doctoral student in Taiwan. He said, Assalamualaikum, Waalaikumsalam, and it was a very interesting lecture, and thank you. He has two questions. The first, in your opinion, what kind of situation we can consider to choose groundwater divided hydraulic boundary rather than physical boundary? Because as we can know, together the hydraulic boundary has possibility to change when stress applied.
Yes, but what is yes, I understand yes, we could have, in fact, we should be monitoring the water table and not only the water table, yes, the pressure at different depths, if possible. So we will be able to know what is the response that the groundwater is taking from the actions that we are doing. Yes, definitely that's a must. And that also, I would recommend you to do it in the vertical scale, because usually, as I was saying, I see that most people have the custom, because it's a custom. People get accustomed to do, let's say, the groundwater evaluation on maps. And I think we need to do it to try to change it and understand. And I see people, even for me, at one time, it was difficult to understand vertical flow and how to measure it, how to do the interpolations to try to get these groundwater flow directions. It was difficult at the beginning because my mind was blocked in the horizontal plane, and then we need to make ourselves understood that, and then from that you will go on very well. I'm sure. But if you need any extra assistance, please contact me. No problem.
Yeah, Gumilar, you can see Dr. Jose email address in his monitor, where gcr@igg.unam.mx. So you can directly discuss with him if you have any question. He's a very nice person, I'm telling you. And the second question from Gumilar, still from Gumilar, the accuracy of the transient model is determined by appropriate selection of the initial condition and also selection of time steps and stress periods. In your opinion, for groundwater contaminant modeling, what is the suitable selection for initial condition, time steps, and stress periods?
Yes, very good question. Yes, for me, when we have been carrying out any investigation in that context, it has to be the original. You need to reproduce the natural, pristine, I think it's called in English, pristine conditions. So that means before any human being was present there. And how can you be sure that you got a pristine conditions? When you go back and go to the library, go to the places where they have newspapers, go to the place where they have ancient documents, and find out how were the conditions in the area that you are interested in. Because usually now we see there are, for instance, no trees. Oh, no, you see there are no trees. No, wait. Let's say 100 years ago, 200 years ago, it was a some woods there, if there was many trees there of this kind, that implies that it was a recharge area, that implies it was a discharge area, that implies the water table was at that position, a particular position. And once you do that, you are able to try to match those pristine conditions. And what about the water quality? The water quality, the original water quality, is also, you have to go in areas which may be in the catchment nearby, or in the upper part of the catchment, when you might have some water quality that might be likely to be the original water quality in the area. Because if you go down to the area where you have already your impact by humans, you will have not the water quality, original water quality whatsoever. So you need to know, basically, from proxies, many times, from proxies, which is the water quality that you might be happening to have. And then I will say these things, just go back in history and trying to find out the pristine conditions. Those are the best, from my experience. And also, when you need to calibrate, you will find that those pristine conditions are just marvelous. They fit very nicely with the rest of the stresses you are going to impose on your model.
Okay, thank you, Dr. Jose. Okay, we still have several questions, but I'm very sorry if I cannot deliver your question to Dr. Jose right now, but I promise you that I will send your questions to Dr. Jose and his explanation. I hope you have time to write your explanation by email, Dr. Jose.
Yeah, well, that's what I worry about. It's easier to explain it.
Because it's almost Zuhur time in here in Indonesia.
Oh, I see. Okay. Sorry for that. Yes.
No. And thank you for coming. And I hope all of us can give our reaction, applause or heart to Dr. Jose for giving us this priceless information today.
Anyway, yes, just before you go, you wish we could meet with some special questions sometime later on. Okay.
And my colleague remind me we will have a photo session before we close this meeting, Dr. Jose.
Yes.
And maybe Mbak Iim will lead this photo meeting session for us. Please turn on your camera. Thank you.
Hello everyone.
Turn
Thank
on
you.
your camera.
All right.
Hidayat, thank you for coming.
Thank you, Professor, for sharing.
Thank you. No, thank you, everybody.
Dr. Hidayat is the head of Research Center for Technology and Water Resources, Dr. Jose. So thank you for coming, Dr. Hidayat.
Very kind of you. So kind. Thank you.
Okay, please. Please start the photo session by.
Okay, I'll count into 3. Please give the best smile of you. We have 3 pages here, so I will take 3 of them. 1, 2, 3. Wait a minute. Second page. 1, 2, 3. Last page. 1, 2, 3. Okay, thank you, everyone.
Right. No, thank you, everybody. And
thank you.
I do appreciate it very much.
Thank you, Prof. Jose.
Thank you.
Thank you very much, Dr. Jose.
Bye.
Thank you.